All right, so we're going to go through chapter 15 or chapter 14, reactions of carboxylic acids. So the first thing that we're going to talk about is we're going to talk about class 1 carbonyls. We're going to talk about this, and we're going to talk about this in the next video. So class 1 carbonyls are anything where we have something of the form COZ, where Z is an atom that is more electronegative than carbon. Okay, class 1. These are the class 1 carbonyls. Acyl chlorides are the best, then acid anhydrides, estrogen carboxylic acid is about the same, and then there's amides. Class 2 carbonyls, next video. Okay, resonance structures. So it's very important to know what the major contributor is when we talk about resonance because these are the things that we use in our mechanisms, right? Like whenever we protonate it here. We don't protonate it here because this is the major contributor. And you might think, okay, why is this the case, right? Because I thought I said that Y is something that's electronegative. So in this case, this is the minor contributor because although there's not a formal charge on this, this is electron deficient. This does not have a complete octet. So having a complete octet will beat out formal charges generally. There's one caveat to that, and we'll get to that in a couple slides. Okay, so these are the major contributors. So these are what we're going to use when we discuss our mechanisms. Amides have higher resonance energy. So resonance energy is the energy of going back and forth between these structures. So a higher resonance energy basically means a more stable structure, and a more stable structure is less reactive. And just as this is the case because nitrogen is less electronegative and it's therefore better able to accommodate the positive charge. It's better stabilized by resonance and has a greater resonance energy. Okay, if you want to right now, pause the video and think about why specifically this is not the major resonance contributor. Okay, so the reason why this is not the major resonance contributor is because halides are really poor bases that do not share electrons well. So additionally, there is very poor overlap between the carbon 2p orbital and the large chlorine 3p orbital, right? So if I looked at a periodic table, right, I would see that chlorine, sulfur, oxygen, sorry, what were we talking about? Oh yeah, Cl is in a different row than carbon. So this is a 2p orbital, 3p. So because of this, because of the sizes being different, spatially speaking, the orbital overlap is really, really bad, which means that the resonance, the pi bond that forms here is really like very like unstable and it just doesn't really happen. So this is our caveat to the octet rule, right? Although the octet of carbon is not filled here and it's technically filled here, having a pi bond is so bad and so unstable and so unrealistic that this is a major contributor. Cool. Okay. All majors, major. Okay. Reactivity of class 1 carbonyls. So class 1 carbonyls have the same approximately basic mode of reactivity. So we have a nucleophilic position, or sorry, we have a nucleophile attack an electrophilic position, C double bond O, polar covalent bond, partial negative, partial positive. Nucleophile will attack here, kick up the electrons. The electrons will come down, they'll kick off the Y group. Sometimes we'll have protonation steps in the middle, depending on what this Y group is. Okay. Relative reactivities of carboxylic acids. So this is just saying that when we are in this intermediate and the oxygens come down, it'll kick out whichever group is the weaker base, right? So we assume that when we do this, we're using a nucleophile that's stronger of a base than this because the more stable base or the more stable conjugate base is the thing that's going to leave, right? So basically, we're just assuming that the Y is a better leaving group than the nucleophile. Otherwise, we're not going to get a reaction, right? Okay, cool. So these relative reactivities can be understood from a lot of different trends. We could simply memorize the pKa's. We could understand the trend of the leaving group. We could understand the conjugate acid of the leaving group and go off of acid-base chemistry. Um, all this to say is there's a lot of different ways to understand the same facts, and the more that we know, the better we are informed to, you know, remember things. In case we forgot about the leaving group trend and we knew the pKa's, we'd still be able to figure it out, right? So carboxylic acid derivative, this is pretty important too, can be converted into a less reactive derivative in a nucleophilic acyl substitution, but not one that is more reactive, right? We go from higher energy to lower energy because the change in energy is then negative, right? If we start at a high and we go to a low, final minus initial, negative delta G. Negative delta G says spontaneous, right? Okay. this reaction will not happen. I think you guys have enough intuition at this point in the course to know that having the Cl come here and kick off the OH would be a ridiculous thing. Okay. Reaction coordinate diagrams. So this first reaction assumes a poor leaving group. So this reaction is, it doesn't really happen, right? Like there's no tendency for this to happen. So all reactions, the first hump just corresponds with the activation energy, right? To get to the transition state. Once we're at this transition state, it's easier to climb up this mountain than it is to climb up this mountain, right? This difference in energy is greater than this distance. And also the starting compound goes to a higher energy compound. This delta G is positive. There's no driving force for this, right? Versus if we look at this here, we go up in energy, activation energy. Once we're at the transition state, though, it's easier to climb up this mountain than it is to climb up this mountain, which means that this reaction is likely to happen. And then we can also see that the free energy goes down, right? Because we're going from a higher to a lower energy compound. Same reactivities here. So when we're in the transition state, we could just as easily go up this way as we could this way. And now I ask you the question, if we have two leaving groups with the same propensity, how do we favor one of them? How do we favor this way or this way? And we'll answer that question in a couple slides. Okay, acyl chlorides, these are just some names. Cool. Okay, acyl chlorides are super reactive. They are the most reactive of the carboxylic acid derivatives. So the mechanisms are slightly different depending on whether you have an incoming nucleophile that's charged or neutral, but approximately still the same. So if we have a charged nucleophile, we'll attack the electrophilic position, we'll kick up, the lone pair will come down, kick off the Cl. Perfect. Great. A neutral nucleophile mechanism, it'll be the same thing, except we have to have one deprotonation step, right? Because if this comes down, we'd rather kick out this than this. So we need to deprotonate this to make sure that this stays on, and then we kick off the other thing. Generally speaking, like when we talk about mechanisms and tetrahedral formations for the transition states, you'll always see a characteristic. We deprotonate the shit that we attach, and we either protonate the stuff that we want to remove, or it's already such a good leaving group that we don't need to. Okay. And specifically, like if we have an acid anhydride or an acyl chloride, we don't need to protonate this, right? Okay. Why do I need two equivalents of amines to make amides? The first equivalent will act as a base, it will act as a nucleophile, attack here, kick this up. The second equivalent will act as a base. So it's important to note nucleophiles are generally considered strong if they're negative, but also nitrogen is such a good nucleophile that we don't actually need to have acid promotion, like acid catalysis or base promoted catalysis for this reaction point to be electrophilic enough for this strong nucleophile to attack. But anyway, the second equivalent just acts as a base. We come down, we kick this off. Okay, and this is no longer a nucleophile because there's no lone pair electrons. Okay, reactions of the esters. There's three reactions of esters. There's ester hydrolysis, there's transesterification, and there's aminolysis. Ester hydrolysis, we have a poor electrophile and a poor nucleophile. Generally, like for these reactions to occur, we need some type of catalysis, which is either acid or base. So we have to make one of these good. We have to either make a better electrophile, a good electrophilic spot, or a good nucleophile, a good base, right? So we make one of these better, and that will catalyze the reaction. Okay. Transesterification. So we're taking one ester and we're replacing it with a different ester. So how do we favor this formation? Le Chatelier says that if I put a ton of excess here, I'll go this way. If I remove this, I'll go this way. So there's two things you can do. You can either remove the alcohol here, or you can add excess of this alcohol. Either way. Aminolysis. So poor electrophile, good nucleophile. If we add heat, we get an amide. Cool. This is kind of important too. In acid catalyzed reactions, when you're drawing the intermediates, everything in the reaction mechanism, if it's acid catalyzed, if it's acidic conditions, you never form a negative. You can have neutral, you can have positive, never negative. And for base, you never form a positive. You can have neutral, you can have negative, never a net positive. Okay, ester hydrolysis, acid catalyzed. So let's walk through it, right? So the first step is making this a better electrophilic spot. From there, this carbon is sufficiently electrophilic for a poor nucleophile to attach here, kick up these electrons. We'll deprotonate from the stuff that we want to keep, the thing that we just installed. We'll protonate the stuff that we want to remove. And then this lone pair, this carbonyl compound, or used to be a carbonyl compound, will come down and kick this off. And we can see that this group is identical to this. So the lone pairs could come from here and kick this off. It doesn't matter. And at the end, we'll have a base workup step, right? Okay. This entire mechanism is reversible. So the way you can think about it, right, is when we get to the transition state, they have about the same leaving propensity, so they could go just as easily this way as they could this way. Okay, cool. So when we're converting from, like groups that are pretty like similar in energies, they're considered to be reversible, right? And that's our alcohols and esters. Hydrolysis of esters, that was the primary and secondary alkyl group hydrolysis mechanism. So it's important to note that um, it's different for tertiary. This undergoes an SN1 mechanism, and that's because we can't get an SN2 because these ties are too sterically hindered. So for a nucleophile to attack here, um, it just doesn't work. So we have a slightly different mechanism where we make this site more electrophilic. These electrons come here, kick this up. We have this. This thing is the carbonyl. This is the OH. And then SN1 mechanism. OH2, H2O attaches here, deprotonate, workup step, final compound. So, when you go through SN1 mechanisms, remember you can get racemization. So this is another pretty easy question to ask about a little of the nuance associated with using a tertiary alkyl versus a primary or secondary. Okay, transesterification. Again, replacing one thing with one ester with a different ester. Mechanism we just went through. Okay. Hydroxide ion promoted ester hydrolysis. So this is ester hydrolysis in basic conditions. So we talked about, oh, actually, sorry, we haven't talked about acidic conditions yet. Okay, acidic conditions, good electrophile, poor nucleophile. Basic conditions, poor electrophile, good nucleophile. Base catalysis, we attack right here, right away, because we have a good nucleophile. So this is a bad electrophile, but it's a good nucleophile, so it's okay. And then these come down and kick this off. This is an irreversible step. We deprotonate, and we're left with the carboxylate, which is really, really unstable. Like, sorry, not unstable. This is really, really low energy, right? It's the very bottom in our trend for the relative reactivity of these compounds. It's not even on the chart. It's that bad. And why is that? That's just because when we have a carboxylate ion, this is no longer, oh, the trend was here, sorry. This is no longer a nucleophile or electrophilic spot, right? This is supposed to be an electrophilic spot here, here, and the rest of them. There's a minus here, so now it's no longer an electrophilic spot. Okay, so that's why the second step is reversible. Transesterification, base catalyzed. The base should always be the conjugate base of the alcohol. Okay, cool. We start here. We use excess of this reagent to favor the formation of this product because again, the reactivity of this and this are approximately equal. The mechanism is what you would expect. Since it's base, we attach right away, we kick this up, we come down, we kick this off. Okay, cool. And then you could see how, like, when we come down here, this can be removed just as easily as this. That's why we use excess of this to favor formation of this final product. Okay, reactions of carboxylic acids, Fischer esterification. So, esterification, we're making an ester. Cool. Fischer discovered it. Cool. We turn a carboxylic acid into an ester. HCl is the thing that acts as a catalyst and keeps the carboxylic acid protonated. So it's just acid catalyzed, right? Mechanism is what you would expect. We protonate to make it a better electrophile. We use the poor nucleophile to attach here, kick this up. We deprotonate the stuff that we want to keep on. We protonate the stuff that we want to remove. Former carbonyl electrons come down. They kick this off. Workup step, final product. Okay. There's also no base catalyzed reactions of carboxylic acids, and this is due to acid-base chemistry. So if we had B minus here, a base here, it wouldn't attach here. It would preferentially attach here. It would just deprotonate this, and now we have a carboxylate ion. We'd have this compound. It would just deprotonate this H, and then it's not reactive anymore. Okay, favoring products, we talked about that. Reactions of amides. Amides are very unreactive, which means that they need really harsh conditions to react. So these two reactions are acid-catalyzed hydrolysis and aminolysis. Cool. This doesn't happen, this doesn't happen, this doesn't happen, right? Because these are all higher energy compounds, right? And we can't go from a low energy to a high energy. with using like our general mechanism, right? We'll talk a little bit later about how we do that though. Okay, acid catalyzed hydrolysis. This is for amide hydrolysis. This is for amide alcoholysis. You're adding a water versus a um, ester. We can look at the mechanism. I'm not going to go through it again because it's the exact same mechanism that we see for pretty much everything in this chapter. Make this a better electrophile. Core nucleophile attacks, kicks up, deprotonate what we want to keep on it, protonate the shit that we want to remove, comes down, kicks off, work up step. Cool. Same thing. Cool. Okay. Base catalyzed hydrolysis of amides. Amide hydrolysis can be base catalyzed. We prefer acid catalyzed hydrolysis though, because um, this is a very unstable. A minus next to a minus is really, really unstable. Electron-electron repulsion. Just keep that in mind. I don't think there's ever a case where base catalyzed is better than acid catalyzed. Base catalyzed always has issues throughout, and I'll point out, like the particular things that I'm referring to as I go through the content. But just as a general note, if you can do acid or base catalysis, you almost always do acid catalysis. Okay, Gabriel synthesis. So before we go through this, pause the video and tell me why this does not serve as a viable way to synthesize primary amines. Okay, so there's no way to stop here. So nitrogen, if you recall, is a really, really good nucleophile, right? So once it attaches here and kicks off the Br, we still have a lone pair. So we're going to keep on going and we're going to keep on getting deprotonations, right? Assuming we have a base to remove the hydrogens, which we will if we're like in water, that's a good enough base to deprotonate, right? Well, actually it isn't, sorry. But anyway, the whole point of this is we will just have a very large amount of difficulty with stopping at the primary amine. So we have Gabriel synthesis. This is a phthalimide. All of this is just a glorified protecting group, right? You can see how much resonance and conjugation there is in this system, which means that it's really easy to deprotonate this H, right? Because of all the withdrawing effects. So in a Gabriel synthesis, we deprotonate the H. We can use something like RO minus, HO minus. It doesn't have to be anything particularly incredibly strong. Um, then we add the alkyl halide. This step is, what you would expect to remove a protecting group with. You use HCl, H2O, and heat. And in the end, you end up with NH3 plus because remember we're in acidic conditions. And we need a workup step to get to the free amine, to this neutral compound. Okay, cool. Nitriles. So there's a lot of issues with adding like NH2, NH3 directly on. So what we need to do is we need to add nitriles and then go through steps to reduce them. Or in synthesis, it's a very useful intermediate. So let's take a look at what happens, right? So this is acid catalyzed. So this carbon is, it's electrophilic because we're getting pulled this way, and like it's not electrophilic enough though. So we attach it to nitrogen, a hydrogen to make this more electrophilic. We attack here, we kick this off, and then we get what we would expect in that we deprotonate the stuff that we want to keep on, we protonate the stuff we want to remove, comes down, kicks up. And to go from here to here, I guess you're not on the hook at this point in the content. You'll realize it's just a simple tautomerization type mechanism. It's pretty simple actually. But anyway, I guess I leave it as an exercise to the reader to go from here to here, mostly because I don't feel like drawing it out. Okay, preparation of nitriles. SN2, awesome. This does not work with tertiary alkyl halides. Again, it's privy to SN2. SN2 does not work with tertiary alkyl halides. Dehydration of amides. SOCL2, P2O5, or POCL3. Any of the reagents will work. Traditionally in this class, we've seen SOCl2. I know that we've also seen POCl3. You're not really on the hook for any of these mechanisms. It's sufficient to just understand that they dehydrate an amide. SOCL2 is also kind of seen as an activation agent. For amides, there's nothing that can activate it, okay? So again, just keep that in mind. Nitriles are useful in synthesis. Renny nickel can reduce a CN to an amino group. You're not on the hook for the mechanism. Just make sure that you know how to predict the product. Cool. Acid anhydrides. So this is the mechanism for nucleophilic acyl substitution. This is the leaving group. It's exactly what you would expect. We attack, we kick up. And again, we can use H2O, the weak nucleophile, because this is such a good leaving group. We deprotonate what we want to keep, comes down, kicks off. Cool. Nothing we haven't seen before. Okay. Dicarboxylic acids. So the the reaction mechanism for this is also basically a tetrahedral. But generally speaking, I think it's generally sufficient to understand how to predict the products. I don't think you're going to have to draw out a lot of mechanisms for these. But all a dicarboxylic acid is, di is two carboxylic acids on the same molecule. So pause the video and guess why the pKa of this is so much lower than this, and how do we get these pKa's to be closer to each other? What happens to get those pKa's closer to each other? Okay. So as the distance between the two carboxylic acid groups increase, the pKa value will also increase because the second carboxylic acid group can better stabilize the minus when it's closer. Make sense? Cool. Okay. Again, it's pretty easy to predict the products. Heat plus this or this. If you see a reaction like this and you're not given one of these reagents, technically you do need one of these, but I think that it's often written as just heat. So keep that in mind when you're predicting the product, like um, just to have as a note. Okay, carbons. One, two, three, four carbons. One, two, three, four carbons. At the one position and the four position, carbonyls are attached. At the one position and four position, carbonyls are attached. This is a dehydration, right? So we lose one H and we lose one OH, H2O. This O, this O, one of these O's. Cool? Okay. This, is just a glorified dicarboxylic acid that just happens to have really good conjugation, right? So the electrons can flow between them. Cool. Okay. And yeah, like I was saying earlier, even though these are technically separated by 1, 2, 1, 2, the reason why this one is so much lower than this one is because this is a conjugated system, so the electrons can flow across. Cool. Okay, activating carboxylic acids. Carboxylic acids are very unreactive towards bases. So there's a couple ways to activate them. We're only going to talk about Stockl 2, but there's a lot of reagents you can use. So Stockl 2, it's an alcohol dehydration agent. You'll replace the OH with a Cl. Cool. Propose a synthesis. Attempt this problem. Pause the video. Okay. This is one of the ways to do a synthesis for this. Again, like there's many ways to do synthesis. Um, yeah, that about wraps it up for the reactions of carboxylic acids.